Hello, good afternoon, everybody. Hope that you have already taken your lunch. Wait for 1 or 2 more minutes for your friend to join us. Yeah, so time waits for no man. So without annexation, let's continue from where we stopped yesterday. So yesterday I introduced to you about crystal field splitting theory, where inside crystal field splitting theory, these are two concepts that you need to know. First is how the metal ion attract the ligand, attract the negatively charged ligand. So it is the electrostatic attraction forces. Okay. Now, because ligand brings a lone pair electron, and this metal ion it has d orbitals filled with electrons, isn't it? So in between the d orbitals, which is illustrated here, the ligand will cause the d electron in the energy levels. It will first rise. Okay. So when the ligand, in this case water, when they interact with the metal ion, energy of the metal ions will be raised up because all electrons carries energy. So as a result, when now because electron is something negative, here is also negative. So in between negative and negative, they will sort of undergoes repulsion. As a result of repulsion, the 3D orbitals split into two energy levels. Okay, so this is how octahedral complex split. Okay, so you split to dx square, dx square, dy square, and then this is dz square. And then in here, the second energy level is dxy, dyz, dsz. Okay, so it will split into two different energy levels. So this is due to the repulsion between the d orbital and the ligand. So when the white light pass through this splitting, okay, so that is how some of the color is absorbed, and the color absorbed in here, okay, because it will cause excitation of the electron from the lower energy level to the higher energy level. So this is how we are going to explain why complex ions are colorful. Okay, so making use of titanium 3 plus as an example, let's together understand how does the complex ion are colorful. Okay, showing to you in here is the valence electron of a Ti3 plus is 3d1. Okay, so when Ti3 plus dissolved in water, it will form a complex of TiH2O6. So that is where we say is that this is when you form TiH2O6, you have a ligand already. So when there is a ligand, so there is a repulsion in between the electrons in the d orbitals of the metal ion. So this will cause the d orbital to split into this will cause the d orbital in the titanium to split into two different energy levels, such as illustrated here. Okay. Okay. So when the d orbitals is split into the two energy levels, okay. So when the white light pass through, the visible light pass through the aqueous solution of TiH2O6 3 plus. So in this case, it is the yellow-green that is absorbed. Okay, in this case, this is the yellow-green color is absorbed. So so when the yellow green is absorbed, so electrons are able to excite from the lower energy level to a higher energy level. So we claim that this is a type of DD transition take place. Okay, so when it's absorbed, DD transition take place. The terms DD transition means that D electron in the lower D orbital to higher D orbital. Okay, so you claim that as a DD transition. Okay, so the one that I had underlined so far in the slide is the important keywords, okay, that you need to explain how does the transition metals are colorful. Okay, so therefore color that is not absorbed is the color that is observed by us with our naked eyes, which is as violet color. So as for the
做烂到这样啊？
不是烂，它晒太阳晒黑掉。
然后有虫吗？
不一样呀，红木熟那里有虫。
关掉你的。有虫，没有虫。
有虫，很大字。
Oh no.
Okay, never mind. Maybe Kelvin Pang forgot off his phone. Off the mic. Okay, never mind. Don't worry, small thing. Okay, so in here, these are the keywords. So the keywords to explain how is the transition metals are colorful. So you must first explain that when the metal ion dissolve in water, you form complexes. So when complexes is formed, 3D orbitals in the titanium ion or in the metal ion will split into two different energy levels. Okay. Then as a result, when when the white light is passed through, okay, when white light is passed through, okay, to the aqueous solution, some of the color is absorbed. So in this case, it's green-yellow color, okay. But you don't need to specific what color is absorbed. You just say some of the color is absorbed. So when this color or wavelength is absorbed, there will be a DD transition. Okay, DD transition take place. So the color that is not absorbed is the color that is observed by us with our naked eyes. So in here, if we absorb this yellow-green, our naked eyes will be observed as a violet color. Okay, so that is how you are going to explain how is a complex colorful in here. Okay, so these are the keywords. I re-explain for the third time again. First is you need to mention where valence electrons inside the 3D orbitals when dissolved inside water or dissolved inside whatever okay, complex will be formed. So when complex is formed, 3D orbitals inside the transition metal ion will split into two different energy levels. So when visible light pass through this aqueous solution, or when visible light pass through the complex, some of the color is absorbed. And in this, when this occurs, DD transition take place. So therefore, the color that is not absorbed with not absorbed is the color that will be observed with our naked eyes. Okay, so these are the keywords. So in order for some of the color to appear, you must have this DD transition. So if there is no DD transition, where the electron from the lower energy level does not excite to a higher energy level, so no color absorbed. Okay, so you must at least have one single electron for a DD transition take place. So what are the circumstances when there is no DD transition take place? So the circumstances that causes no DD transition take place is when, number one, the d orbitals are empty, or number two, d orbitals are complete filled. Okay, so there is still splitting. Okay, there was anytime whenever you already form complexes, the splitting is still take place. However, if the d orbitals are empty, okay, or the d orbitals are complete filled, so the electrons are not able to excite. Okay, so that is what and when there is no DD transition, no color is absorbed. So this substance in solid they will seen as white color. In aqueous solution, most of the time they will seen as the colorless solution. Okay. So this is how we are going to explain this. Okay, can you give me 1 minute? Sorry. Hello, 不過什麼代誌啊？
我就問你，你早啲講發電嘅，我都問你喎，叫人去公告會樣嘅咗。
冇咧，跟住一個卡電話可以，打個卡電話可以，打個卡落去啊，係成啊，我做咁樣例子。冇代志啊，冇什麼啊，冇什麼。有什麼嘢物件什麼興了了，你買嘅物件是嘢紅骨嘅物件嘛？嘢紅骨嘅物件興了嗎？有見得就我打卡電話問伊啫，我做我大部代志啊，睇下不過啊，係啊。Yeah, sorry for the disturbance. Okay, so there will be no transition metals. If the transition metals have no electron, or the d orbitals are completely filled with electrons, then there will be no dd transition take place. So this when these complexes, when in solid, they will observe as a white color solid, and then in liquid, they will be observed as a colorless solution. Okay, so simple as that. So this will explain why compounds such as SCH2O6 3+ or CuCl2- are empty, because in SCH2O6 3+, so scandium 3+ is scandium originally is 3D14S2 So when scandium 3+, so the 3D is empty, or copper is originally 3D10-4S1 So when you form Cu+, okay, so 3D is complete field. So when it is empty or it is complete field, so no DD transition take place. So that is why you observe as a colorless solution in here. Okay. So that is how we are going to explain how complex are colorful. That's it. Okay, so don't have to trouble yourself to remember what I explained to you yesterday. Okay, the most important thing is the today's one to explain how is the complex colorful. That's all. Okay. Okay. So these are a few complex ions that are colorful. Some of the very basic color that you try your best to remember are this few. Okay, chromium 3+ is very common, green, and then this one is also very common, orange. Okay, Cl2O72-. Okay, these two are very common in STPM. And then MnH2O62+ is actually Mn2+. Mn2+ is light pink, MnO4- is purple to light pink, the manganate ion. Okay. Then other than this color that you try your best to memorize, this one, iron. Iron, you have three colors that you have to memorize. One is green, this one. Then another one is yellow. You can also say FeH2O6 is brown, never mind. And then another one is this one, FeH2O5 SCN2+. This one, the oxidation state is +3. I think I already corrected inside the notes already. This is +3. Okay, so red blood solution. Okay, and then cobalt. Cobalt not important, never mind, not important. Okay. Then nickel also not that important. Nickel is somehow green, at least try to remember Ni2+. Ni2+ is green. Copper, all color, try your best to remember. Okay. Copper, all color, try your best to remember. Okay. Okay, so that is all that you have for this one. Nothing much already. Okay, so try to remember all the transition metals that I highlighted just now. I repeat which one that you need to remember. You need to at least remember for chromium 3+, green, Cl2O72- orange, Mn2+, light pink, MnO4- purple. And then iron, you must remember iron 2+, iron 3+, green and yellow, or green or brown also can. And then FeH2O6 5 SCN. Okay, so this one, blood red solution. red blood solution, whatever. Okay, and then nickel is green. Copper, you have to remember copper in aqueous solution is blue. This CuNH3 4 2+. Tetraamine copper 2 ion is dark blue, and then CuCl4 2- is actually green lah, not yellow lah, green. And then CuEDTA is light blue. Okay, so that's all. No, the rest of the color no need to memorize. Okay. Okay. So with that, that is all for the transition metal ion, and we are going to do some study case on when will a complex ion become colorful. So there is this one last factor that you need to know: how can a complex changes its color? So these are the three important key of how transition ions change its color. Number one, you need to first understand what is a stability constant of a complex K. Okay. Okay, complex ion undergoes ligand exchange or substitution in the solution. The rate of this reaction depends on the nature of the metal ion and the ligand. In the study of ligand exchange, reaction is often used to distinguish between the stability complex ion and its tendency to react. So, in order to understand how stable or complex is, you have a stability constant that you need to know what it is. So, in the stability constant, let's say this is the equation that you use to form complexes. Mn plus X ligand give MlXn plus, which is the complex. I repeat, this is the metal ion. This is the ligand. This is a complex. So the stability constant of a complex K is measured by the complex divided by the concentration of the metal ion multiplied with the concentration of the ligand. Okay, so if the K is high, means that you have more complex. That means this complex is more stable. Okay, and conversely, if the stability constant is low, means that you have the concentration of the metal ion or the ligand is very high. So that is why this complex is not stable. Usually, this stability constant has a very large value. So instead of expressing as a stability constant, we express as a log stability constant. So here are a few examples of how you are going to write this one. Okay, so for example, if you want to write the complex ion, how does the complex ion FeCN6- is formed? So FeCN6- is formed by Fe3 plus 6Cn minus give FeCN6- if you want to express K is equals to, this one I didn't express, so you might want to write on your own. K FeCN6- over Fe3 plus multiplied by Cn negative power of 6. Okay, just on how you write Ka, Kb, Kc, and etc. Okay. Okay, the stability constant is 1.0 times 10 power of 42. So FeCN6- okay, so this is the equation, the metal ion, the ligand, and the complex. CONH3 6 2+, so it's cobalt 2+ plus 6 ammonia to form the complex. AlF6 3-, Al3 plus 6F minus give AlF6 3-. Then copper 2+, Cu2+ plus 4NH3 gives CuNH3 4 2+. Finally, CO2+ plus 4Cl- gives CuCl4 2- here. Okay. Okay, so because our stability constant are usually very large value, you see that? So that is why we don't express as the log constant. We usually we don't express as the stability constant K. We express as the log constant K. So in log K, I think the books are already write out all the value for you already. So no need to this one. Okay, so here are a few things that you can compare in between this stability constant. What are the few things that you can compare? You can compare in between the first equation and the second equation. Here. You see that they are almost the same. However, the first equation has a larger value than the second equation. Why are they different? Because of the oxidation state. Then the second thing that you can also compare in here is this one. COH2O6 NH3 and this one, this one. They both have the same cobalt ion, as you can see here. But their stability constants differ widely. Okay, so it seems that CONH3 6 2+ is more stable than COCl4 2-. So why are they like that? we have the look at what are the factors that will influence the stability constant in here. Okay, so first one is the oxidation state. So usually we say that greater the oxidation state, higher the stability of the complex form. So this is due to as the charge becomes greater, so the charge density becomes stronger, so the ligand attached to it will become more stable. Okay, so this is the first reason. Then the second reason is the type of ligand surrounding. So stability of the type of ligand increase from monodentate to bidentate to polydentate ligand. And then for polydentate ligand, there is a special terms for it. The special terms in here for a polydentate ligand is what we call as a chelating effect. So when we say it is a monodentate ligand, can you imagine? So I put, if you look at the video camera that shows you right now, monodentate ligand is one claw. So you try to hold this marker pen. When you try to hold this pen with a single finger, will it be very stable? It will not be stable, isn't it? Then if you have a bidentate ligand is two claw. Okay, two claw. So this complex ion hold better in here. So it makes the complex more stable. And then polydentate ligand, it is like you have many fingers, you have many claws holding to these objects in here. So this will greatly increase the stability of the complex in here. So that is why we say that monodentate ligand is the least stable, followed by bidentate ligand, and the polydentate ligand are the most stable. Okay. And polydentate ligand holding to a center metal ion, we have a special effect. We call it as a chelating effect, chelating. Chelating. The way of how we pronounce is chelating effects. Okay, so these are the two major reasons of how we did manage to identify the ligand. As teacher, just now the Cl minus and the NH3 minus one, how teacher? So if you still remember, yesterday we managed to discuss the strength of the ligand here. Strength of the ligand in here, isn't it? So the strength of the ligand is based on this one, the one that I just show you right now. Okay, so the strength of the ligand from a monodentate to a bidentate. Okay, so these are the strength of the ligand. Okay. Okay, so that is why in here just now you see Cl is lower, isn't it? Then ammonia is higher, isn't it? Okay, because ammonia is a stronger ligand compared to chloride ion. Okay. Okay, so with that, that is how you are going to determine the stability constants and the effects towards oxidation state, and also the type of ligand surrounding it. Okay. Okay, so in here we are going to see a few study case on how do we can we see the color changes in here. So we are going to see one by one what are the study cases and how do we deduce these changes of the ligands in here. Okay, are you ready? Okay, case study number 1. Anhydrous copper 2 sulfate is white color solid. When dissolved in water, it turns to blue solution. When a small amount of the copper 2 sulfate is added to concentrated hydrochloric acid, it turns to green. However, when this complex is added to excess water, green solution form back to the blue. And when ammonia solution is added to the blue solution, a blue precipitate is first formed. And when added to excess, blue precipitate solution dissolves and turns to a dark blue solution. So when a few drop of sodium ethylene diamine tetraacetate, which is EDTA, is added, solution turns to pale blue. So I'm going to show you a video that will help you to understand how does this color changes for copper. Okay, so I'm going to show you the video right now. Okay, so Now, what are we going? What can we see from the video right now? Is now we try to add this. This is plain water lah, plain water. Okay, so when we put okay, so we are going to put a hydrated. Now, the hydrated color is blue color already. Just now, if you read the beginning statement, anhydrous. Anhydrous means that no water. No water, it is white color. But now, this salt itself that I showed you in the video right now is already hydrated. That means contain water. So that is why it is blue. Okay, so when this blue hydrated salt, I added with concentrated hydrochloric acid. So look at what happened after I added with concentrated hydrochloric acid. Okay, so when some of the hydrochloric acid is added to the blue salt, okay. Okay, do you see that it turns to green color? Yeah, it turns to green color. I don't know whether you can see at the down video there. Okay. Now it gives green color. Do you see that? So this green color is due to the CuCl4 2-. Now, towards this green color solution, I'm going to add plenty of water. So look at what happened after I add plenty of water. It turns to the blue color solution back in here. Okay. Okay. So this is what happened when added to water. Okay, so now I'm going to show you another video of what happened when copper sulfate is added with when copper sulfate is added to the sodium hydroxide and ammonia. Okay, so I'm going to show you ammonia. Yeah, so I straight away shows you for ammonia. Okay, so now look carefully at this video. Okay, so what I'm going to show you in here is what happened when a little amount of ammonia is first added, then followed by excess ammonia. So when a little ammonia is added to the copper 2 ion, okay, immediately you see a blue precipitate is formed, isn't it? So this blue precipitate is due to the formation of the copper hydroxide, CuOH2. Okay, okay. So you see the blue precipitate in here. Okay, apparently I already accidentally mixed quite a lot already. So that is why down here you can see they start to form blue, deep blue already. Now I'm going to add excess ammonia in here. So when you add excess ammonia, immediately you can see that the blue color precipitate dissolve and turns to dark blue solution. Okay, so this dark blue solution is due to the formation of CuNH3 2- in here. Okay, so I hope that the video is clear for you just now. And then last but not least, when you add a little EDTA, then you form a pale blue, which is I don't have the video for that. Sorry for that. Okay, so here is the explanation. So when there is no water ligand surrounding, there is no splitting of the DD orbitals, so no DD transition take place, which explains copper sulfate anhydrous. Copper sulfate in here must be anhydrous. The word anhydrous means that no water. Okay, that means it not yet formed complexes. So that is why when some water is added, you form a CuH2O6 2+. Okay, so this is the one that caused the blue solution. Okay, and then as we mentioned just now, when concentrated hydrochloric acid is added, the water is displaced by Cl-, but this is only true under concentrated condition. If dilute, cannot. If dilute, cannot. Okay, you must only have concentrated solution. Then you form CuCl4 2-, which is a green solution. However, under excess water, okay, at first you form the green solution in here. Okay. However, when excess water is added, then the reaction is reversed. Okay, you add excess water, then you form CuH2O6 2+. Okay. Now, in the second video that I showed you just now, when ammonia is first added to the copper 2 aqueous solution, you form a blue precipitate. So this blue precipitate is due to the formation of CuOH2, copper hydroxide. This H2O4 you don't write also, never mind. The most important thing is CuOH2. And when we add to excess ammonia, okay, so the blue precipitate dissolve and form another dark blue complexes of CuNH3 4 2+. So this is to the equations. So why is it like that? Because ammonia is a stronger ligand than water. Okay, ammonia is a stronger ligand than water. Okay, and finally, when we add a little sodium EDTA, so because EDTA is a polydentate ligand, so it will able to displace the ammonia to form a more stable CO EDTA 2-, which are pale blue in color. And since it is a polydentate ligand, so it has a chelating effect take place as it has many core that is bonded to the center copper 2+ ions. Okay, so this is the equations. So this is how we are going to reason why is there changes of the color in the complexes in here. Okay, so I hope that you'll be able to understand. If you still cannot understand later, I send you the video. You can see the video again. Okay. Okay. Then the second study case is when anhydrous copper 2 chloride is blue color. Anhydrous means that it is no water. Okay. So when it added to a small quantity of water, the solution turns pink. And when the hydrochloric acid is added, the solution forms back to blue color. And when cobalt ammonia is added to the ammonia, it turns to pink solution. And when added to potassium cyanide, it turns to deep red. Okay, what am I going to show you at the upcoming video is only until here. It's only until here. After I add hydrochloric acid. First, I add water, then I add hydrochloric acid. Okay. Okay. So now I'm about to show you the second video for the study case number 2. Yeah. Okay, so I want you to look at this video carefully. Okay, so in here, the first salt is dissolved inside ethanol, inside alcohol. This alcohol does not have water. So when it does not dissolve in water, it is first, it's a blue color salt. Okay, blue color salt. Okay, so this blue color salt is now not yet with water. The scientists dissolve in alcohol. So when some water, just a few drops of water is added, okay, you can immediately see that the blue color solution starts to turn to pink color. Do you see that? Just a few drops of water. Okay. Okay, so both of them are water. Then the scientists add some HCl. Look at what happened when you added to concentrated HCl. So after the scientists add concentrated HCl to the cobalt aqueous solution, the cobalt solution formed back to the blue color. So the blue color in here is the COCl4 2- in here. Okay. Okay. So this is about the copper, and I can only show you these 2 videos only for the cobalt. Okay. Okay, and last but not least, the third study case in here is this one. So the explanation is sorry, the explanation is due to when copper ion dissolved in water, you form a COH2O6 plus, which is a pink color. And when pink color of the COH2O is added to the concentrated chloride ion, you form the COCl4 2 minus, which is the blue color solution. Okay, so when added to ammonia, you form slightly deeper pink color. It is still pink, but it's deep pink. And finally, when you add it with cyanide ion, you form a red blood solution. But this one is not important. The most important thing is the above two. These above two equations are the most important explanation. This one. Okay. Yes, yes.
Yeah. Why can the chlorine ion displace the water? Since
yes.
Water is a stronger
from the strength of the ligand that we see just now, chloride ion is a weaker ligand than water, isn't it? That's why I stress the word concentrated. Okay, concentrated chloride, yes, you can displace. Because according to the equilibrium, according to the Le Chatelier principle, when the concentration of the chloride ion increase, okay, so when we equilibrium shift to the right. So this is only true under high concentrations only. Understand or not? Okay. So when it is dilute, okay, you add water, you dilute back, then the equilibrium will shift back. So that is why in here you see that, yes, I already mentioned just now, chloride ion is a weaker ligand compared to water. However, if you use concentrated chloride ion, so it will cause the equilibrium to shift to the right. So that is why you are able to form this complex ion of COCl4 2 minus because of the high concentration. Okay. However, if you add back water, equilibrium shift back to the left to form the complex ion back. That's all. Okay. Okay. So that is for the second study case, and the third study case is the iron 2. So when iron 2 sulfate is added to plenty of water, green solution of the hexaaqua copper 2 hexaaqua ion 2 is formed. And then when added to this iron 3 ion is added to potassium cyanide, so you form a yellow solution. And when this iron 3 is added to the few drop of potassium cyanide, it form a blood red solution. This one I'm so sorry, I don't have video for it. I just have some photography only. Okay. Okay, so I show you the photo. Because this one I don't have video. I try to find, but I cannot find the video. So I just can show you the color only. Okay. Okay. This is a okay, so this is iron 2 aqueous solution. Okay, iron 2 aqueous solution, green in color. Then this one is iron. Okay, sorry. Then this one is iron 3. Okay, so iron 3 is yellow. You can say brown, brown in color. This is iron 3. Okay. Actually, this experiment you already do it in your STPM level, isn't it? Okay, and then this is what happened when iron 2 and iron 3 added to potassium hexacyanoferrate. Can you see the video or not? Can I think no problem. I'm still sharing the video. Okay, so this is what happened to the cyanide when the hexacyanoferrate 2 is added to the aqueous solution. Okay, so when it's added to Fe3 plus, you form the blue. Oh, no. Okay, this is not this one. Sorry. Okay, nothing already. Okay, sorry, wrong this one. Okay. Okay, so with that is all for the things that you need to know. So I'm going to end my lesson for today. So tomorrow, I will continue with the final part of the transition elements, and I will finish the syllabus tomorrow. Okay, so see you all tomorrow. Thank you very much.
Thank you, teacher.
Thank you, Mr. Chu.